Hello everyone, in a recent video I critiqued the Sunbird Fusion spacecraft which you see here. It is from Pulsar Fusion, this is pulsarfusion.com, and I didn't really go into a whole lot of detail about the math involved or how fusion propulsion actually works. I just pointed out some of the more obvious things, like no matter what there's going to be waste heat, so they need radiators. And actually, the spacecraft needs to be shaped in a very particular way if they want it to not irradiate the payload, but we're not going to go into that. I'm just going to discuss in this video how fusion propulsion works as far as spacecraft are concerned, and what that tells us about some of the other flaws about this design. So here we have one of my little calculators that I've made with Claude AI and ChatGPT. So as far as the specific numbers are concerned, I'll point out which ones I think are okay and which ones we might want to take with a grain of salt. It's mainly for illustration purposes at the moment. It's not on my website yet. And I'm going to continue to investigate whether certain numbers, especially the mass budget, are correct. But for now, it'll give you an idea of what we are talking about when we are talking about using fusion propulsion on spacecraft, because it is a very arcane topic, and it's one that maybe needs to be broached since people are making claims about it. I mean, if people are going to be trying to get funding for it, maybe we need to nail down a few things, because we're going to see that there are certain other questions about that spacecraft that we need to talk about. So the first thing we have is a variety of different reactor classes here, and these mainly set the mass of the system. They're not going to change the specific impulse, which is the efficiency of the system, or the thrust. Mostly, the specific impulse and thrust are influenced by the amount of power that is put into the thrust. There's a trait. The specific impulse is pretty much determined by your fuel cycle, what you're actually going to be fusing, and they were going to be using deuterium and helium-3, which is somewhat aneutronic. It's not as aneutronic as the proton boron. Aneutronic means that it's not producing as many neutron radiation particles, which means that you don't have to protect as much from that kind of radiation. There are other kinds of radiation, like gamma rays, X-rays, and stuff like that. This one that I can hardly pronounce, brimstralong, some energy is going to be wasted in that. So it's limiting a certain kind of radiation, which is helpful and makes fusion better than fission in that respect. Fusion will have less radiation. Fusion also automatically sort of shuts down if you can't sustain it. There's not much possibility. I don't think there's any possibility of a runaway reaction. So they are using this cycle, which is a little bit tough. It's tough to activate deuterium and helium-3. There is this plasma temperature, and you have to have the plasma temperature pretty high, but not as high as proton boron would require. The easy one is deuterium-tritium. So that's the idea there. But as we see here, deuterium-tritium gets less specific impulse. So we're just going to go with that. But the reactor class is going to tell you how this stuff is being confined, and that determines the dry mass of the system. Now you might notice that here we have a net electric of negative 0.2 megawatts. Well, that's not good. So let's bump that up so that we have a reaction that's actually going to give positive power, and we can sort of moderate the plasma temperature there. We get about 2 megawatts. That's what they said for Sunbird. Here we have a disturbing amount of installed mass. That's mainly because we're using a stellarator, which is meant to provide large-scale electric power. The one that most matches what they seem to be talking about is the inertial Z-pinch. Unfortunately, if I tune that down, the minimum I can get is 15 megawatts right now. So I need to add some lower chamber radius to the core parameters there. But we can also tune these factors with the Z-pinch. These have a big influence, the pellet fuel mass and the burn fraction. I don't know if this is what they intend to use for their system, but here we get 2.5 megawatts. Still an installed mass of 47 tons. Now, papers I've read have said that they could get specific power of about 180 kilowatts per ton. And so if they're getting 180 kilowatts per ton, and we're looking for, let's say, 10 times that in the net electric, though it's not clear to me whether they were talking about the average fusion power or the net electric, but let's say it's for the net electric, then in that case, we could probably swing it in 10 tons. But that's a lot for such a small spacecraft. So we have to take that into consideration. Now, somebody said, well, they gotta watch out for how they're going to mount this thing. Otherwise, it's going to be like a missile into the Starship. Well, first of all, it shouldn't be used on Starship. But second of all, it's not got that much thrust. You know the 0 newtons that we've got here? Well, that's worrisome, isn't it? The thing is, the little particles that are going to be generated by the direct fusion system, it's deuterium and helium-3 combining into helium and a proton, plus a lot of energy. These are going to go out the back at a certain speed. Just like when you combine hydrogen and oxygen together in a hydrolox chemical engine, you know you're going to get a certain exhaust velocity basically in the same range. You're going to get it in a tight range around 440 seconds, so plus or minus 30 around that is the idea in vacuum. Same idea. If you're going to select a fuel cycle, you're going to get a certain specific impulse. But there's like a million. It's actually 1.1 million that we can tell by the exhaust velocity here. And so what do you do with this? You get all your energy as great exhaust velocity, but not much thrust. They're just a little bit... you're only shooting out a little bit at a time. It's like a few particles here, a few particles there. Well, the solution to that is to inject more particles. You're going to let these super energetic particles that have been fused together push all the rest of the particles, basically like an afterburner. So what we do is, let's collapse some of these. We, in the drive nozzle, add our afterburner. And so you can see with this propellant augment, we get to reduce the specific impulse and then increase the thrust. It's a direct relationship. The more you increase, the more thrust you want, the less specific impulse you get. But they didn't mention that, did they? They had this sort of regenerative propellant thing. There's no space on the spacecraft for this propellant that they're talking about. And we need much more than this mass flow multiple of 40 in order to get the thrust that they want, 10 newtons to 100 newtons. And get down to the specific impulse they're talking about, 10 to 15,000 seconds of ISP. But it's a direct trade-off, so if they want the thrust, they need to sacrifice the specific impulse by injecting the propellant. And they didn't have any storage for that. They didn't mention what it was. And the ion thrusters on board, the Hall effect thrusters, I should say, are going to be using something like xenon and noble gas. That's not really a good thing to use in the fusion system, but it would be convenient because at least it's dense. And you're not looking for a whole lot of efficiency out of the system anymore. You're basically looking for thrust, and the heavier xenon particles will give you the thrust. But it's good for simplicity, but it's not really what people generally think of using in a fusion drive. Normally, if you're going to be doing anything with the propellant augment, you're putting in hydrogen or deuterium. And both of these are voluminous. So that's the rub. Now, they're carrying deuterium anyway, but the fusion process only uses a tiny bit of it. That's why the propellant augment's going to end up being in the hundreds, maybe even 1,000. And so you're going to have to dump a whole lot more deuterium in there to get the thrust and specific impulse that they specified. As we also get better efficiency as far as material technology, we see that the masses go down and our specific power goes up. The mass does not include the radiators right now or the ship's shadow shield. So this is not including any protection from radiation or the need to expel the heat. This 30 tons is just how much the actual structure is going to take in terms of the magnet. But it's still something I'm looking at because I'll have to take a look at more papers. But then again, papers are papers. They haven't actually built the fusion system. And between the paper and when they build things, as we discover with practically all space technology, the masses get inflated. So they go up. And we have to worry about that. But anyway, one thing you don't have to worry about as far as the Sunbird fusion system is it's not going to be much of a missile. At initial acceleration here, 0.003 millimeters per second squared. That's based on this spacecraft and radiator thing. So Starship's dry mass is whatever, well, let's say with the system attached, well, let's just say 100 tons. We're not going to include Starship with too much propellant. So, okay, 400 tons with its propellant, not including, well, anyway, let's set that aside. But that's the acceleration. Not good. So we're not too worried about it. And that's why it probably shouldn't be pushing Starship around. It's not going to give you a whole lot of thrust. And so what exactly are you using it for? Well, as I continue to work on designing what this system would really look like, the Sunbird system, what would it really look like? We will explore exactly what it might be for. And it should be its own cargo vehicle. It's better to imagine it as its own starship, not as something that's pushing some other starship. So it'll have a cargo bay in front, and it'll have its radiators, and it'll have its little thruster, and maybe also a supplementary orbital maneuvering system. They showed RCS on the thing, though they didn't mention how it ran, and their little 3D model didn't even show the indication of RCS thrusters. But in the graphic where it left its little docking pad, they had RCS. If we see here, we do see some puffs occasionally. There's a little puff. Somebody said they saw 8 thrusters on it. I don't see. I only see an upper one and a lower one. Maybe some these on a nose count, but they're still not. Oh, are they puffing? The problem with them is that as it turns, they're not turning it, right? That's anyway. That was the thing that annoyed me. It seemed like these Hall effect thrusters were the ones that were turning it, and there was no puff that was actually turning it that way. But these are not placed properly in order to turn it. Those Hall effect thrusters, unless they gimbal, maybe they gimbal, and they're supposed to gimbal. But that's a whole other topic. So anyway, I hope that this gives you a better idea of how the fusion drives would actually work. And the key thing is they're going to expel their little particles at a certain specific impulse, and you're going to have to inject other particles to get some thrust out of it. So that's the problem. And with the Sunbird, we wonder where exactly is the propellant going to be then? So that's another problem aside from the radiator problem. So all right, that's just a discussion on fusion propulsion. And with that, thank you for watching. I hope you enjoyed this video. If you did, please do press like. If you have any comments or suggestions, please leave them in the comment section below. And I'll see you next time.